Welcome back to Code in Motion, everyone. Today we have another fun LeetCode problem, number 100, same tree. Given the roots of two binary trees, P and Q, write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. So in this case, you see P and Q, not only are the numbers the same, but the shape is identical as well. We only have 3 nodes, one on each side. For this example, even though we have nodes 1 and 2 and the values are the same, note that the shapes are not identical. This 2 is part of the right subtree for node 1, whereas this 2 is part of the left subtree for node 1. And then the last example, we have 1, 2, 1, 1, 1, 2, where the shapes are identical, but the numbers at 1 and at 2 are different so that the trees are not equal. Let's get started with the algorithm. First, we're going to start at the root nodes. So this is 1 for P and Q. In this case, they're equal. If P and Q values were not equal, then we could return false. We know that the trees are not equal. The trees are not equal if their numbers are different at a specific node, or if they're a different shape. So ones are the same. That means we have to check if the left subtrees are equal, right? So this is a recursive call. Let's recursively check if the left trees are equal. Now we go to node 2. Node 2s are equal, so once again we check if the left subtrees are equal. So we go to node 3. In this case, once again, these nodes have the same value for P and Q, so we check if the left subtrees are equal. Now we finally hit our base case of null. If you have 2 nodes that are null, then the trees are the same, right? This is your base case. It's only not going to be the same tree is if you have one node that's null and another node that's not null. But in this case, they're both null, so the trees are the same. So let's go back up to node 3, and let's check if the right trees are equal. Once again, they're both null. So in this case, at node 3, the values are the same, the left and right subtrees are equal, and so the current subtree at node 3 is the same as well. So let's put true and go back up to node 2. Now we're at node 2, we have to check if the right subtrees are equal. So we go to node 4. The values are the same, so now we check the left subtrees, which is null. The trees are the same. And then the same thing happens for the right subtrees. They're both null in this case, so the trees are the same. Now we know that at node 4, the trees are the same, so we put true, and we go back to node 2. Now at node 2, the values of P and Q were the same, they were both 2, and the left and right subtrees were also equal. So now we know that the subtree at node 2 is also equal, and now that means that the left subtree at node 1 are equal. So this is true. Now, for 1, we recursively check the right subtree, which is 5. Once we're at 5, we check the left subtree, which is 6, and we continue the same exact process as we did on the left side. We check the nulls. In this case, they're both null, so it's true. And then we check the right side as well. They're both null, so the trees are the same. And so at node 6, it's true. The trees are equal. Now we go up to 5. In this case, we have to check if the right trees are equal. And this is where we actually find the interesting part of the problem. One node is null, the other node is not. And so this is actually how we detect that the shapes are different. The only way for the binary trees to have different shapes is if you eventually get to a null and not null node situation. So the trees are different in this case. And so that means the current subtrees are not the same. And so the trees are not equal at node 5. This propagates back to node 1, and eventually we get false as our final answer. The trees are not equal. And this algorithm runs in O of minimum nm time and space as well. What is n and m? Well, n is the length of P, m is the length of Q. In this case, the reason why it's the minimum of those two is because we eventually stop processing on the smaller one, right? Because eventually we'll find out that they're not equal. So that's why we take the minimum. Now, the reason why you have space complexity being the minimum of n and m is due to the recursive stack. So how many recursive calls are we going to make? At most, it's going to be the minimum of n and m in a skewed tree. I love coding out binary tree solutions because the code is pretty minimal lengthwise. It's actually just difficult to understand how you're going to use recursion and what conditionals to check. But coding it out is pretty quick. So let's start with the base cases. If not p and not q, then return true. This is saying if both of the nodes are null, then the trees are equal. However, if only one of them is null and not the other, we return false. So if not p or not q, return false. This is checking that the shapes are equal or not equal. Besides the shapes being equal, we need to check that the values are equal, right? So if p.val does not equal to q.val, we return false because the values are different. Now at this point, if we didn't hit any of these conditions, that means we have two nodes that are not null and the values are the same. So now we need to make sure that the left subtree is equal and the right subtree is equal. So left equal is equal to self.is same tree, p.left, q.left. Let's make sure that the left subtrees are equal and that the right subtrees are equal. So right equal is equal to self.is same tree, p.right, q.right. Return left equal and right equal. Now there is an optimization over here you can make in Python and other languages. Right over here, if the left subtrees are not equal, we could just return back saying false because we already know there's no need to process the right subtree. But having the code structured this way will check both. If we really want to optimize this, we could do something like this. And Python is smart enough to know that if this is false, we won't run this code. And so this is kind of like a shorthand trick you will see sometimes in LeetCode solutions where people only check one side in order to return back quicker if the left side is not equal because there's no reason to process the right side. Let's run this and see if it works. And there we have confirmation. Thank you so much for watching. If you're interested in more LeetCode style animated videos, especially for the blind 75 list, feel free to subscribe and like the video down below. Thank you so much, and I'll see you in the next one.